and caffeinated for the next couple of hours. We're going to begin with an invited talk by Nanase Harada on molecular cloud evolution and astrochemistry in nearby galaxies. And welcome.
Okay, thank you very much for the introduction. First, I'd like to thank the organizers for inviting me to this exciting conference where we can look forward to the future. My name is Nanase Harada from NALJ, and I've been working on astrochemistry or multi-transition molecular line studies in external galaxies. And today I'd like to talk about how we can extend this study with ngVLA and SKA. So this is the outline of my talk. So first, I'll make an introduction and how we can use astrochemistry to study the ISM properties, and then now apply to different galactic environments, such as different galactic structure, or at the place of extreme starbursts, AGNs, mergers, and extremely obscure nuclei. So as this schematic picture shows, the astrochemistry may be related to evolutionary stages of molecular cloud as it gets denser and denser from a diffuse cloud. And it's also related to external environments such as massive stars, AGNs, and supernovae. So I'll just go through one by one. So as far as the evolutionary stages go, of course, the atomic gas gets condensed and form molecular clouds. And so they are pictured like, like each one shell collides with each other to form molecular clouds. And I think this talk on Thursday may be somewhat related to this. Correct me if I'm wrong. And after the medium gets fully molecular, carbon may take different forms, such as ionized or atomic or carbon monoxide. And when atomic carbon is still abundant, we have abundant carbon chains. And later on, we started to see nitrogen-bearing molecules, deuterated species. And when protostars are born, the mantle ice mantle can evaporate, and you start to see complex ionic molecules. And there's a chemistry talk for individual protostars by this morning. And I guess many of you know what photodissociation region is. So that's the region where UV photons are abundant from massive stars, and you see increased abundances of ions and radicals. Around the AGNs or young stellar objects, you have X-ray dominant regions, or you have efficient heating and also ionization and dissociation. And this can penetrate farther than UV photons. And around supernovae, you also have high energy cosmic rays. And gamma ray telescopes are better at probing high energy cosmic rays, but not so much for lower energy cosmic rays. But lower energy cosmic rays, you have a higher ionization cross-section. That means, and ionization is the one that changes chemistry. So our hope is that by studying chemistry, we can study lower energy cosmic rays. And cosmic rays, especially the higher energy ones, it can penetrate farther than X-rays. So there are also regions where things are affected by shocks. So those are supersonic waves caused by outflows, supernovae, cloud collisions. And there, the temperature can increase to thousands of kelvins. And there you see species like SiO, because of the sputtering of the elemental, like silicon from the grain core, and ice, sputtering of ice, such as methanol. Okay, let's look at the real astrophysical sources. And I think, so many of you are probably interested in the distribution of atomic hydrogen and carbon monoxide, which traces molecular gas. So I think there is a poster also about this. So with SKA and ngVLA, we can observe atomic hydrogen with higher angular resolution than we can currently do. So with that, we can compare atomic hydrogen distribution, which is more abundant in outskirts of the galaxy, and compare with atomic gas, molecular gas, like the one that can be observed with ALMA. And as you can see from this movie, the spiral galaxies, in the spiral galaxies, the gas flows into the spiral arm and go out from the spiral arm. So it doesn't just stay on this spiral arm region. So as they do this, they can form stars when they go through the densest region. And so this picture in the middle shows higher excitation at the downstream of the spiral arm. So with new telescopes, we can study these difference in excitation, for example. And we can also see shocked region at the outside of the correlation radius. So the correlation radius of this galaxy is around here. I'm not showing the two sides. And so there, outside that, you see higher methanol over 13CO ratio shown with magenta. So it shows the spiral shocks in this galaxy. So that's with ALMA, and with ngVLA, we can do this for more sources. Okay, so because stars form in dense gas, people have observed HCN because HCN has higher critical density than CO, and there has been a correlation, so there's this correlation of HCN and star formation rate, and tracing dense gas is raised as one of the key science in ngVLA memo series as well. But there's this recent study, relatively recent study, that says that in galactic molecular clouds, HCN is quite extended. So if you look at the chart here in the upper top right, so red is the most diffuse one, and the blue is the most dense one. And if you compare the fraction of where it comes from, CO and HCN, they do not change as much. But for NTH+, it actually comes from the densest regions. So NTH+ might be a better tracer of dense gas. So to test that, we wanted to observe not just central region, but the off-centered region of M83 with ALMA. So this is just preliminary maps of NTH+ and HCN. And just to do this, we needed the on-source time of 12 hours. And it's impossible to do that for the entire galaxy, obviously. The telescope wouldn't give us that much time. So, and NTH+ is 3 or 4 times weaker than HCN. So we need ngVLA. And with ngVLA, we can do that because ngVLA can probably do this 15 times faster than ALMA, despite the smaller field of view. Okay, so let's move on to the starburst region. So we have been conducting this ALMA large program, Alchemy. So it's from cycle 5, and it traces, it observes a very nearby starburst galaxy, NGC 253, in the central region. And so this is the spectra, and as you can see, we see so many weak lines. And to do this, the time in the band 3, which is the 3 millimeter band, so on source time was about 5 hours per tuning. But with ngVLA, we can do that 30 times faster. So obvious thing to do is to observe northern sources as bright as ngVLA, as bright as NGC 253, and we can also extend to many more sources. And with wide bandwidth of ngVLA, we can do this kind of spectral scan more efficiently. So one thing we could observe from this survey is complex organic molecules. So complex organic molecules are carbon-containing atoms, molecules with 6 or more atoms. And one example is ethanol. So we detected ethanol for the first time in extragalactic sources. So the ratio of ethanol over methanol in the top panel is equivalent to that of galactic hot cores. So hot cores are protostellar sources. So these complex organic molecules could be originated from either shocks or hot cores, but because the ratios are similar to hot cores, we might be looking at hot cores with this ethanol. So what is good about SKA and ngVLA is that we can go to lower frequency, and it's better in terms of line blending. So we can observe these large molecules more efficiently. And our study also shows high cosmic ray ionization rate, 1,000 times higher than that of galactic disk. And we did it with multiple species, actually. So we used H3O plus over SO, and we also used a molecule called HOC plus, which is a metastable isomer of HCO plus. And we saw a strange morphology for HOC plus. So there's a hole here. Well, I cannot point here, but anyway. So it's a location where we see superbubbles. So superbubbles are location of expanding H2 regions or supernova remnants where you have so much energy that it creates cavity. And this CO channel map with higher angular resolution from another group so identified the bubbles, and this HOC plus hole looks exactly at the same location. So this molecule is tracing a very peculiar region. Okay, so we also derived physical conditions such as column density, volume density, and temperature. So we did this with large velocity gradient analysis coupled with hierarchical Bayesian analysis, which seems to work better than maximum likelihood analysis. And we could constrain them well because of formaldehyde as a good temperature probe. Unfortunately, ngVLA doesn't have formaldehyde lines, but they have good ammonia lines. So coupling with other transitions, we can create these maps with ngVLA as well. Okay, we could also trace shocks, and some of the shocks come from orbital. Shocks are at orbital intersections. So because NGC 253 is a bar spiral galaxy, gas on the bar orbit flows into the central region, and there's another central orbit. So when they collide, we expect shocks. So we saw things like class 1 methanol measure, which is shock excited, and we also saw HOCO plus unexpectedly. So you may not be familiar with this molecule at all, but this is a protonated CO2. So we think that CO2 ice is evaporated because of the shock. And after protonation, we observed this So it's enhanced at the location of these cloud collisions. And some of the shocks may be coming from the star formation as well. So SIO 65 come from the regions of starbursts, not at the orbital intersections. And when I looked at the peak after this fun et al. Was accepted, I realized that the peaks correspond with locations of peak signal profiles detected with high angular resolution observations. And so those peak signal profile means that they have outflows, probably cluster scale outflows. So these shocks traced by SIO 65 may be from this starburst. And we also did some statistical analysis of many moment maps, and we compared the radio recombination lines with many other molecules, and the distribution looked, the molecules that looked most similar to radio recombination line is the transition of CN or CCH with higher excitation. But for lower excitation, they only trace extended diffuse regions. So to trace the central starburst, we may have to go higher excitation PDR tracers, not the lower excitation one. But unfortunately, ngVLA nor SKA can trace these higher excitation lines, so we may have to look for another tracer. Okay, so we were also doing some analysis for starburst-driven outflows. So NDC 253 has an outflow that had been already identified. So we also did some analysis of 12 CO over 13 CO, and the ratio looks quite high as the elemental abundance of 12 C over 13 C observed in the literature. So that implies optically thin nature of this outflow. And it relates to the mass estimate. So that should be important, and that can be applied to other galaxies as well. And back in '85, there's this OH plume detected in the same galaxy, but the locations are different. So this OH plume may be tracing another phase of the outflow. So yeah, looking at it again with ngVLA must be very interesting, and also for other galaxies as well. And yeah, we are preparing these moment maps for release. And let's move on to AGNs. Okay, so both simulation and observations have shown that atomic carbon over molecular carbon monoxide is a good tracer of X-ray dominated regions. But neither ngVLA or SKA can observe atomic carbon, so we probably need a good tracer to trace X-ray dominated regions, perhaps OH. That's a job for theoreticians. And so AGNs also launch outflows, and in these outflows, so this is the 3mm continuum that's actually mostly synchrotron for this galaxy. And around that, molecules like CCH, CN, and atomic carbon is enhanced. So that may come from shock dissociation or some irradiation. And well, we know that ngVLA and SKA, we can go to very high angular resolution. So of course, it's very interesting to trace the very vicinity of AGN. So with the parsec scale observation, they saw torus with HCN 32. But even with higher angular resolution, same transition, they saw counter-rotating structure within that. So that shows the benefit of higher angular resolution. And I also note that CO65 may have more contamination from outflows, so HCN must be a good tracer for the torus structure around AGNs. Okay, so let's move on to majors. Majors. Sorry, I'm confused. I'm confusing myself. Okay, so obviously, atomic gas is a good tracer of tidal tails with higher angular resolution. We can compare these better with simulation because you have better kinematics. And going into the central region, we can do the similar analysis with what we did for starburst galaxies. And we also did some ALMA observations. So this source is a merger, and northern one is face on, the southern one is edge on, and the structure looks like this, but methanol only traces the interaction regions of the mergers. And another group did the study of methanol over certain CO versus depletion time, and it showed that higher ratio methanol shows higher depletion time, meaning that they have lower star formation rate. So these interaction regions have lower star formation efficiency, but eventually this gas must lose angular momentum, so it might eventually lead to star formation at the central region. Okay, so I want to finish off with extremely obscure nuclei. So some contents are from Suzanne Otto from Chalmers, and so there are extremely compact obscure nuclei. So the column density may be 25th per square centimeter or so. So it's highly obscured, and it's hard to see what the energy source is. So that might be AGNs or extreme starburst. And they have extremely bright vibration-like excited lines. So the upper state energy may be hundreds of Kelvin to thousands of Kelvin. And fairly good fraction of ULERGs, about a third of them, are from have these extremely compact obscure nuclei. And I'm also a part of this, but so we did some observation of cons with 20 milliarc second survey, and if you look at the HCN vibration of the excited lines, they are rotating structures with the radius of 3 to 8 parsec, and they also show features of outflows. So these are extremely dense, extremely hot, and it has some association with outflows. Okay, so it looks like the perfect time to end. So this is my summary slide. So with ngVLA and SKA, we are able to study different parts of the galaxy, not just the central regions, but the outer outskirts with multiple transitions. So, and these are the tracers that we can use. So I highlighted the species that can be observable with ngVLA in blue, and oranges are some things that we can also do with SKA. And of course, the SKA can come earlier than ngVLA, so that has some advantage as well. So thank you very much for your attention.
happy to take a question.
That was a very nice talk.
Thank you very much.
Quick question. You mentioned a lot of lines that also aren't in the ngVLA SKA that are in the ALMA, right? And so I'm very curious about how all of these telescopes are going to work together. I'm curious if you've given it a thought as to, do we need to get our act together now and do an awful lot of work with ALMA, because once SKA and ngVLA are online, they're going to be able to do so much so quickly? Or are the strengths of these lines such that all the telescopes are going to need about the same amount of time? Or I'm just trying to understand where we're going to be in being able to put all of it together.
Yeah, it's a very good question. And some of the lower frequency transitions, it's very hard to do with ALMA because even if the brightness temperature is the same, it takes much longer to do with the lower frequency range. But with ALMA, you can do it with reasonable amount of time. So if we need to do some combined analysis of higher frequency range and lower frequency range, both ALMA and ngVLA, SKA, these are great combination.
Hi, thanks for a great talk. I was wondering about the starburst outflow that you showed in NGC 253, right? So can you say something about the dynamical structure? Like, I mean, I understand that the geometry is bad for you to estimate a wind velocity or something like that, but are there estimates to do that?
Estimates of geometry?
Like something like the wind velocity. So how fast can the wind escape in such a case?
I think the projected velocity is 400 kilometers per second. Okay.
So is it slightly inclined that you can estimate that, or how?
So this galaxy is almost like AGNs. So yeah, the actual velocity change is only like 80 kilometers per second or so. But if you deep project it, it's like 400 kilometers per second.
Okay, good, thanks.
Thank you for the talk. So I have a comment and a question. The comment has to do precisely with this slide. No? So when we try to measure the optical depth in the part of the outflow that is coming toward us, we measure it with a 2:1 to 1:0 ratio, and we got ratios that are optically thick, not optically thin. So here we are trying to do something different, and it's very difficult to do because the 13 CO is in principle very faint. So you should be careful with the recovery, the flux recovery for this, in this very complicated region for the finite. But let me, you can reply to that if you want, but I wanted to ask you the other question, which is can you accurately measure a cosmic ray rate using the chemical ratios here?
Well, so what we measure is the cosmic ray ionization rate. So in order to get the flux, you have to assume the energy spectra. But okay, so it's challenging because the ionization rate chemistry is dependent on the cosmic ionization rate divided by density. So it's also important to have density estimate. But if you have very good density estimate, if the chemical model is correct, I think we can get an order of magnitude estimate.
Okay, thank you.
Thank you very much.
Let's thank our speaker and we'll move on.